Okay, continuing with the partial fraction decomposition, we're going to ramp up the difficulty here with these examples. The first ones we looked at had linear factors. These are nonlinear and or repeating factors. What that means, going over the different types of factors you can have, a linear factor just means that if you were to graph the factor that's in the denominator, like right here I have a factor of x plus 1. If I were to graph y equals x plus 1, that would be a line. So we call it a linear factor. Same thing with 2x minus 3. If I were to graph y equals 2x minus 3, I would have a line with the slope of 2 and a y-intercept of negative 3. So those are what we call linear factors. And if you have linear factors, it makes the partial fraction decomposition a good bit easier. The other two types of factors we're going to have are nonlinear, which nonlinear simply means if you graphed them, you would not have a line. So like x squared plus 1, if we look at that factor, it doesn't factor anymore. You can't break that down any further. If you were to graph y equals x squared plus 1, you would have a parabola, not a line. Same thing with x cubed plus 6. That is a cubic function. It is not a line. So those are what we refer to as nonlinear factors. We also have something called a repeating factor. And a repeating factor simply means that the factor occurs more than once, and we usually designate that with an exponent. So x minus 2 actually happens twice because it's being squared. X squared plus 1 is a repeating factor. It happens 3 times. And so with repeating factors, that just means that the factor is being raised to a higher power than 1. Maybe I should write than 1 right there. Higher power than 1. And if a factor is repeating, it has nothing to do with whether or not the factor is linear. So notice here I have a linear factor, x minus 2, that's repeating. Here I have a nonlinear factor, x squared plus 1, that is also repeating. So we have we have repeating factors right here. We have nonlinear factors right here. And then we have the simple linear factors that are not repeating. And that's the ones we've already done. So let's talk about how we're going to set up this partial fraction decomposition. It's not as easy and straightforward as it was for the linear non-repeating factors. And remember that whatever the degree is of your original denominator, that is how many constants you're going to need to solve for. So looking at this one, if I were to expand this out, I have x times x squared. That would be x cubed plus a bunch of other stuff, which tells me that I'm going to need an a b, and a c. So I'm kind of have that in the back of my mind. I know I need 3 constants. And setting this one up, I see 2 factors. Now there is the problem, because I have 2 factors, but I need to find a way to squeeze 3 constants in those 2 factors, or in those 2 fractions. Notice my first one is just your straight old normal linear factor. It's x plus 3. That is a line. It's not repeating. So that one's going to get the normal treatment we've been given it. We'll just stick an a on top of that. Now x squared plus 1, that's where my b and my c both have to occur. And the way we set that up is we will do, if it's x squared, on top we'll put bx plus a c. And the top degree needs to be 1 more than the bottom. If it's x squared on bottom, I need a bx to the first on top. And I think I have one coming up where I have like an x cubed on bottom, and I'll show you how to set that one up. So that is how we're going to set up. I'm not solving this one just yet. This one has a little star by it. That means we're going to come back and we'll actually solve this one, but I'm just wanting to set them up for now. All right, here's another one where we have 2 repeating, not 2 repeating, we have 2 nonlinear factors. Again, I'll look at it and I think if I were to expand this out for number 2 here, I would have x squared times x squared, which is x to the 4th, which means we will need an a b, a c, and a d. So we're going to need 4 constants on this one. But again, I only have 2 factors. So I'm going to have one fraction, x squared plus 1, and another fraction, x squared plus 4. Now both of these are nonlinear, and I've got to get 4 constants in order to get this to work. I have an x squared, so on top I need an ax plus a b. This one has an x squared on bottom, so on top of this one I'm going to continue cx plus a d, and that's our setup for the partial fraction decomposition on this problem. And this one will, if you wanted to, we're not going to solve this one, but if you wanted some extra practice, this one should solve kind of nice. Your A, B, C, and D should be nice answers. So if you wanted to try this one, and you can come in and ask me questions if it doesn't work out for you. All right, so number 3, again, I'm going to first find the degree. If I were to multiply out my bottom, I'd have x times x cubed. That's an x to the 4th, which again means I'm going to need an A through D when I set this up. Now my first factor is simply x. So I have something over x plus, and then I have something over x cubed plus 2. Now I've got, let's see, x is a linear factor. If I were to graph the line y equals x, it is a line. So since that's linear, we're just going to put a normal a on top of it. Now the x cubed plus 2 is a little bit hairier. Remember I told you that if it's nonlinear, if you have a nonlinear factor, the numerator needs to be 1 less than the denominator as far as the degree when you're setting up the partial fractions. So if I have a degree of 3 on bottom, I need an x squared on top. And so what I'll do is I have my a, I'll call it bx squared, and then I'm just going to count down on my exponents, cx and d. And that allowed me to get all 4 of my constants in the setup. So there's how we're going to set up the nonlinear factors. Now we need to look and see what we're going to do when we have repeated factors. So here's number 4, and we're going to come back and solve this one later. But let's just set it up for now. We have an x minus 2. That's a linear factor, so this one's not going to be too tough. That's your normal straight up linear factor. It's not repeated, nothing funky going on. So I know that it's going to start off with something over x minus 2, and since that's just a straightforward linear factor, I'll go ahead and put an a over that. Now my repeated factor is the x plus 1. There's my repeated factor. It's x plus 1 squared. That's repeated. And before I go on, let me find the degree of the denominator. If I were to multiply all this out, I have an x times an x squared. That would give me an x cubed, which means I need an a, b, and a c to solve for here. Now, when you have a repeated factor, the trick is you're not going to do the bx plus c trick. What we're going to do, since it's x plus 1 squared, what we do is we start with x plus 1 to the first, and then we count up until we get to the exponent that's in the original denominator. So if it's x plus 1 squared, then we'll have an x plus 1 and an x plus 1 squared. And then on top of each of those is going to be a b and a c, and that allows me to get my a, b, and c in the setup. So for the repeated factors, you just count up. You start with 1, an exponent of 1, and then you count until you hit the exponent that's on the factor. If this was x plus 1 cubed, then I would have x plus 1, x plus 1 squared, and x plus 1 cubed. You count up until you get to that exponent. So we are going to come back and solve this one later. And let's see, I have 2 more examples of this. X and x plus 2 cubed. If I were to set this one up, I have 2 factors. My first one is just x. That is a linear normal factor, so I'll put something over x, and that's just going to be a. That is a linear factor. So x is linear. Now x plus 2 cubed, that is a x plus 2 cubed is a repeated factor. So here we have that repeated trick. And if I distributed and multiplied all this out, I have x and x cubed. That would be x to the 4th, which tells me that I need a through d in this setup. Now if it's x plus 2 cubed, that means we count up until I get to that exponent. So x plus 2 cubed, I'm going to need an x plus 2 to the 1st. I'm going to need an x plus 2 squared. And I'm going to need an x plus 2 to the 3rd. And if you look at those fractions, I have 3 more. I need b, c, and d. So I'm going to put a b, a c, and a d on top of that. Number 6, and I'm about to alter number 6. I'm going to change this to x squared plus 1 squared, just to show you what happens when you have a nonlinear repeated factor. Well, let's multiply this out. I have x squared squared. If you have x squared squared, that would be x to the fourth, and then I'm multiplying that by x squared. So x to the fourth times x squared is x to the sixth, which means I'm going to need an a, b, c, d, e, and f. I'm going to need 6 different constants for this one. Now the x squared, you could treat that 2 different ways. I'm going to treat it as a linear factor of y equals x being repeated. So I'm going to consider that repeated, and I'm going to start out by writing that one. I have x squared, so I'm going to start off with x to the first, and then I'm going to count up until I get to its exponent. So I have x to the first and x squared. And now I have x squared plus 1 all squared. So I'm going to start off with x squared plus 1 to the first, and then x squared plus 1 all squared. And I'm keeping in the back of my mind, I need 6 letters. Let's see, so this is a linear factor. X is a linear factor, so since it's linear, on top of that, I'm simply going to put an A and a B. Now, x squared plus 1 is nonlinear. Now, I know it repeats, but it's a nonlinear factor, so above that one, I'm going to need to do the cx plus d treatment. My top degree needs to be 1 bigger than the bottom, since that's a nonlinear factor. This, again, is nonlinear, so I've got the d. Now I'm going to do ex plus f, and that's going to be how we'll set up number 6. So there is the setup on those types of problems. You have repeated and you have nonlinear factors, and so there's how we're going to set up the partial fraction. Now we need to try to solve them. Okay, so this is the very first problem we did, and we've already set this one up. So I'm going to show you what happens when we try to solve. Just like the other partial fraction problems we've done, we're going to start by multiplying everything by the common denominator. So I'm going to multiply everything by x plus 3, x squared plus 1. So let me do that real quick. There we go. And then we want to see what cancels. My first fraction on the left side, everything's always going to cancel if you set it up correctly, leaving me with x squared plus 7x plus 2 equals, over here, x plus 3 cancels x plus 3, leaving me with a x squared plus 1. And then x squared plus 1. X squared plus 1. And right here you need to be careful with your parentheses because it's all of bx plus c times x plus 3. Okay, so now that I've gone through and I've canceled my denominators, the next thing I want to try to do is see what can give me a 0. I want to plug in a value of x that's going to cancel something, and what I see first is a -3 because that's going to make x plus 3 0. So I'm going to plug in -3 and let's see what happens. That'd be -3 squared is 9, plus 7 times -3 is -21, plus 2 equals a times -3 squared is 9, plus 1 is 10, plus dx plus c, and -3 plus 3 is 0, which is nice because that means my bx plus c term is going to cancel completely, and now I can solve for a. 9 minus 21 is what? -12, plus 2 is -10, equals 10a, and that means my a is -1. And so I plug in -3 for x, and that gave me -1 for a. So now that I've done that, I need to go back and see if I can cancel anything else. And you cannot make x squared plus 1 equal to 0. That's impossible. But what I do see is I see b times x. If I can plug in 0 for x, then I would have b times 0, and that'd be kind of nice. So let's see what happens if I plug in 0 for x. That'll be 0 squared plus 7 times 0, plus 2 equals a times 0 plus 1 plus b times 0 plus c times 0 plus 3. And we'll clean that up. But now you may notice we have 2 variables. We have an a and a c. So what I'm going to do is I'm going to take the value of a. Since I know a is -1, I can plug that in for a right here. A is actually no longer a constant. And so I may even go back to the beginning, and I'm going to take out my a, way up here, and I'm going to go ahead and put -1 in its place because we've already solved for that. And I'll do the same thing right here. I'm going to take out that a, and I'm going to plug in -1. So that gives me 2 equals -1 times 1 plus c times 3. And when you solve that, you're going to get c to be 1. So now I know that c is 1. And since I know what c is 1, I can actually go back up to my original equation, and I can plug in 1 for c. So now it's -1 for A. I know 1 is C. We still need to solve for B, and this is where it's going to be kind of weird because there is nothing else I can plug in to give me a 0. I've already plugged in 0 to cancel my B. I plugged in -3 to cancel this. I need to plug in something else. So what I'm going to do is I'm just going to pick a random number and see what happens. I've plugged in 0 and -3, so those are off the table. Let's just plug in 1 and see what happens if I plug in 1. If I do that, I have 1 squared plus 7 times 1 plus 2. Oh, great, announcements. Equals -1 times 1 squared plus 1 is 2 plus, then I have bx is 1, so b times 1, plus 1 for c, and then 1 plus 3 is 4, and then we're going to clean that up and we can solve for b. 1 plus 7 plus 2 is 10 equals -2 plus, I'm going to distribute my 4b plus 4. And then if you solve that for b, you will get, let's see, move the 2 over is 12, subtract 4 is 8, divide by 4, you get 2 for b. And then once you finally have a, b, and c, we'll plug them back into the original equation. It was a over x plus 3, so -1 over x plus 3 plus, and then it was bx plus c. b is 2x plus c is 1 over x squared plus 1. There is our final answer. So solving these is a little bit more difficult because it's not always possible to zero out all of your terms. All right, and the final problem. So I just paused the recording for like 2 hours, so I really don't know what I just finished doing what to you was a few seconds ago. All right, this problem. Here we had a repeated factor, and this was number 4 that we set up earlier. We have one linear and one repeated factor, but just like every other partial fractions problem, what we're going to do first is multiply every fraction by the common denominator, so x minus 2, x plus 1 squared, and we'll multiply everything by that. So I'll pause it while I set that up. There we go, and we'll start canceling. On the left side, as usual, x minus 2 cancels, x plus 1 squared cancels, leaving only with your original numerator, so 4x squared plus 3x plus 5 equals, over here, x minus 2 cancels, leaving with a, x plus 1 squared, plus, here I have x plus 1 to the first, and x plus 1 squared. This is only going to cancel one of the two. So for b, we're going to have x minus 2 and an x plus 1, but only one x plus 1. And then for the c, x plus 1 squared is going to cancel the x plus 1 squared, leaving with c, x minus 2. And now we're going to look at this and see if we can solve for a, b, and c. I'm going to look at my factors and see what gives me a 0. And looking at this first one, I know if I plug -1 in for x, I will get a 0 for that term. So I will start by plugging in -1. If I do that, -1 squared is 1, so 4 times 1 plus 3 times -1 is -3 plus 5 equals a times -1 plus 1 is 0 squared plus b times -1 minus 2 is -3, -1 plus 1 is 0, c times -1 minus 2 is -3. Then we start cleaning that up. 4 minus 3 is 1, plus 5 is 6. And then my a and b terms will cancel. So a times 0 squared cancels, b times 3 times 0 cancels, and we're left with -3 times c. And when you divide by -3, you get c to be negative 2. So now I know what C is. Now I need to cancel something else. Let's see what else I can cancel. I've already plugged in negative 1. If I plug in 2 for x right here, 2 minus 2 is 0, so that's going to be the next thing I plug in. Let's plug in 2. You want to get as many zeros as you can. Let's see, so 4 times 2 squared is 4, plus 3 times 2, which is 6, plus 5 equals a times, what am I plugging in? 2. 2 plus 1 is 3. 3 squared is 9. Plus b times 2 minus 2 is 0, which means it really doesn't matter for this next one. 2 plus 1 is 3, but that doesn't matter because I'm already multiplying by 0. And then c, I am being multiplied, let's see, 2 minus 2 is 0. All right, so look here, my b's cancel and my c cancels, leaving me with 16. 4 times 4 plus 6 would be 22, plus 5 is 27, equals 9a. And that gives me an a value of 3. So now I know that a is 3. Let me erase that. I know c is negative 2. Now the problem is there is nothing else I can plug in that will give me a 0. I've already plugged in negative 1 for this factor. I've already plugged in positive 2 for this one. And then I see negative 1 and positive 2 again. I've already used those. So at this point, this is when I'm going to go back. I know that a is equal to 3, so I'm going to take out my a and I'm going to plug 3 in. I know that c is equal to negative 2, so I'm going to plug in negative 2. And actually, I'm going to go ahead and rewrite my equation down here. It's 4x squared plus 3x plus 5 is equal to 3. I'm plugging in 3 for my x, plus 1 squared, plus, I still don't know what b is, negative 2, whoops, x minus 2. X plus 1 plus c, which is now negative 2. So I'm plugging in for c, x minus 2. And now I need to solve for b. So this is where I'm just going to pick some other number for x to plug in. If I can plug in 0, I will. And since I have not plugged in 0 yet, I'm going to plug 0 in. It makes it a lot easier. 4 times 0 plus 3 times 0 plus 5 is just 5, equals 3 times 0 plus 1 squared is 1, plus b times 0 minus 2, and 0 plus 1, minus 2 times 0 minus 2 is negative 2. And now we clean up and solve this equation. There we go, and I paused it to solve that. Now I look back up at my original equation, and remember we want to rewrite the fractions, and we're going to substitute in our values of a, b, and c. So I had a over x minus 2, and a was 3 over x minus 2, plus b, which was 1, and b is over x plus 1. And if you want to put it to the first power, you can. And then I have c, which was, where did c go? Negative 2. And c is over x plus 1 squared. And so that is our final answer. Finally! It's been a long time since you've had one this long. How exciting.